All right. Example 4. Let's go. Oops. So here we have it. You have a light illuminated, right, with monochromatic light of wavelength 365 and current I. For this PD, find the maximum Ke of the electrons. Next, deduce the work function of the emitter, and then find the IV graph, which uses twice the light intensity but the same wavelength. Okay. So the maximum Ke of electrons depends, in my revision just now, on the stopping potential. Okay. So stopping potential is 1.5 volts. To measure the energy of electrons, which is the Ke, you use the convergent energy. The loss in Ke is equal to gain in EPE. Remember the applet that I showed you. That gives us this equation. Because the maximum Ke will be the stopping potential of all of the electrons. So that you measure no current. Sub in the equation, sub in the values, get this answer. It's pretty easy. Next, they ask you what's the work function, right? Is it? Sorry, they ask you what is the work function. So if you know the wavelength of light, do you know the energy of a photon? If you know the wavelength of light, do you know the energy of a photon? The answer is yes. If you know the wavelength, you can find the energy of a photon. If you know the energy of a photon, that's the person who's giving you the energy. You're asking how much energy is taken away. Well, you just look at how much is left over, which is the energy of the electron. So you know what is coming in, energy of photon. You know what is left over in the energy of electron. You can find out how much was taken away by the work function. Right? So simply is this. You are given the wavelength and not frequency, so you must learn to convert. Rearrange with the work function as the subject. Sub in the values. Get answer. Okay. So this is 3.0 times 10 to the power minus 9 joules. If I ask you to express it in EV, are you able to do it? You divide this value by 1.6 times 10 to the power minus 19. So you get around 1.8 EV thereabouts. Okay. Part C, you double the intensity but have the same wavelength. What do you think will happen? First, you double the intensity at the same wavelength. What happens to the number of electrons? Sorry, number of photons per second. What happens? I heard something. This side, what? This side, can you answer? Left side. If you double the intensity but keep the frequency the same, what happens to the photon rate? It doubles. Okay? If you double the photon rate, what happens to the electron rate emission? What happens to the middle? What happens to the electron rate? It doubles. What happens then to the current being measured? It doubles. Right? There you go. Done. Easy peasy. Okay? Now, can you try example number 5? Can you try example number 5? I give you 3 minutes. It should be doable. I'll walk around and check. Please try. Alright, let's start. So part A, you actually don't need any equations to solve. Why? Because if you know what is a work function, you know that by definition that is the minimum energy required to emit an electron. So the higher the value, the higher the energy of the wave of the electron you need, of the photon. The higher the value here, the higher the energy of the photons you require. Okay? And the higher energy E equals to HF, the higher the frequency is required. Okay? So is that? You don't need to copy our. Actually, copy lah, go ahead, copy. Take photo or whatever. But you can use your own phrasing, it's fine. As long as it makes sense, can already. Don't need to copy word for word. There's no skill in this phrasing. I just state it as it is. There's no skill required. Right. Part B, they ask for the minimum frequency that will produce electrons from each surface. So you just apply the equation, right? Work function is HF naught. But the F naught for each metal is different because their work function is different. Right? The work function is given in terms of energy. So all you do is sub it in. Okay, let's just wait a while. There's still people copying. I mean, this is recorded. I can go back and copy if you want to. Okay. I'll post it up ASAP. Okay. So part B, using the work function equation, work function is HF naught. But in this case, I want to differentiate the F naught for aluminium with the F naught for calcium. I give them different frequencies, but you must know what we are solving for. So this F is the minimum threshold frequency for aluminium. This F is the minimum threshold frequency for calcium. Just sub and you get these answers. Okay. So you should have done it, right? This question number 5 is actually fairly simple. It's actually one of the more basic ones. Right? Is to get you accustomed to doing. Okay. Next. They ask you, okay, any questions at this point? In fact, if I'm going too fast. Part B, any question? Part C, does calcium show a photoelectric effect when orange light? Can you change that? The question, can you change? 680 is more red light than orange. So can you change it to red light? No, sorry, I didn't check that. Right, the effect is for red light. Lambda equals 680 is more red light than orange. So for the wavelength of 680, the equation of the energy of the photon E equals to HF equals H0 lambda. You get this value. Is this value smaller than the work functions? And the answer is yes. It's smaller. Since it's less, it cannot cause any photoelectric effect at all. You're shining on it, no electrons come out, no matter how long you shine on it. Alright. Questions? Can. You found lambda here, is it? You found the frequency, then you use the lambda change to frequency lah. And you found that it's lower. Can. Good. In fact, that's a faster method, yes? Or just change this to just use F, very good. F equals to C over lambda. sub this in, you find this part. You find that the frequency is lower than the minimum frequency required. Done. Yes? Good. In fact, it's faster. Fmax class. Okay. Okay, use the fastest method. Okay. Question? Yes, Sarah? Oh, I thought you had a question. Good. So with that, we've come to the end, right, of the lecture. But since nobody brought up this question, let me ask you this question. These are both IV graphs, right? Is it okay to curve this way? Is it okay to curve this way? Which way is correct? Actually, we don't care, right? But we like this curve more. We like the S curve more, right? Because that means that there are more electrons near the middle of the pack, near the middle speed, middle energies. So the S curve is nicer. This curve, not so good. But if you see it in the Cambridge, you just accept it. Okay? Second, can you see this? The maximum current is not hit when the voltage is 0. Do you see? The maximum current, so this graph will continue with a straight line over here. Okay? This graph will continue with a straight line over here. Your friend in the other lecture group asked a very good question, which is this. So I want to share with you all. Hey, why you never let me do? Okay? He said, okay, this one starts here. But if I look carefully, isn't this line, the current, not flat? You look here, it's more or less flat, right? If you look above at the graphs I've given you, it's completely to here. So what gives, right? What's correct? What's correct? Cannot be one correct, one wrong, right? It's physics. Actually can. Okay. Some textbooks do it like that, as shown here, right? Some textbooks do it. Some textbooks, that one can erase again. Some textbooks do it like this, where it's completely straight. So why? Why is it like that? Let me explain to you. Anyone of you have this question ever? But just very shy, don't dare to say. Anyone? No, nobody. Just accept, it's okay. So actually, you need to look at the design, right? So the question is this: why is it sometimes it's like that and like that? Why is it sometimes it's like that and like that? Oh, this one too much. Why sometimes it comes out faster? Where this is 0 volts and ampere. Okay, so it comes to the design of the setup. So let me explain this one first. Okay. If you look at the emitter and the collector, when the wave comes in, what happens? The electrons can move in a variety of angles. Can you see? Some electrons are not captured by the collector. So if I set this as neutral, you will have some electrons not being captured. Do you agree? That is why in some Cambridge questions, this is the graph you get. So why did I say that this is also correct? Both of them are correct. Because in some design of collectors, it's like that. The emitter is here. Sorry, the emitter in capital E. Sorry, another curly E. It's here. This is the tube. The design of collector is like that. All encompassing. So for most angles, you'll collect it. So this is for this. It's also correct. Now the question is then why later on you'll reach some certain value. It's because that when you, let me now change the color some more. Let's make the diagram even more complicated. Now if I add this, give it some positive charge, the electrons will then curve back in, attracted to the plate. So at some positive charge, right, the plate C will be so positive enough for it to reach the saturation current. Then you can capture all the electrons that's produced. Okay, can? So it's a minor point. Some textbooks use one way, some textbooks use the other. When I first started out with a picture, I thought that this is the only correct picture and this is wrong. I thought. But when I checked more textbooks, I realized depending on the setup, it can mean either way. And it's very negligible. Well, it's quite negligible. So we are not going to fuss too much about it. All right, that's it. Okay, so now let's do the tutorial. Okay. Tutorial time. Can you take out tutorials, please? Okay. Let's do question 1, A, B, and C in the next 4 minutes. Okay, 4 minutes to do A, B, and C. Oh, this is actually good, really very interesting. As I walked around, some students are like doing question 12, is it? Behind. Wow, respect, very good. Some even finish already, just sitting there and chillaxing. Respect. Wow. Very good. Okay. So question 1, why don't all electrons have the same? Well, basically it's pretty much bookwork. I mean, your teachers will send this to you, so no need to copy, right? Mainly it's because the electrons are emitted from different depths. Right? The further you are emitted from, although the incoming energy is the same, the amount of energy you pay to the metal is different. The work function is only for those at the surface of the metal. Okay? Part B, they ask you, why can't the eye detect this continuous beam, this continuous nature of beam? It's actually for your own sanity, right? If you can detect this continuous beam, it means what? I mean, okay, you look at this light now, there's about 10 to the power 19 billion, 10 to the power 19 photons. 10 to the power 19 photons, that's a lot. If you can detect this continuous nature of it, means your brain is processing 10 to the power 19 things per second. That's quite insane, if you ask me. Second is for self-preservation also, right? There's a minimum amount of light, right, for the eye to see. When you see this, when you look at me and you see me, what are you seeing? Me? No, but it's actually, right, your photons reaching your eye, and the eye converting that to electrical signal, and the electrical signal being read by your brain, and your brain reforms the images. So what you're seeing is actually your brain reforming those images. It's quite cool, you know. You're not actually seeing me directly. I mean, right, you're seeing the image of me in your brain. Right? But what actually sees me is actually your eye. But what you see is actually what actually you really picture. So actually there is some, if you have a brain damage, right, then you cannot see properly. Second, our eyes also function, so wait, I was trying to say this, I got distracted away. The eye requires some minimum amount of photons before it gives an electrical signal. If I see one photon, if my eyeball then fires an electrical signal, I'm wasting energy. Because for every photon I see, I fire electrical, I'm not even sure if that is a significant source of light. So the eye waits for enough photons to accumulate, to see enough, and say, okay, enough photons have hit me within a period of time. I say, okay, that's a source of light, then an electrical signal is sent. So there are some people with more sensitive eyes. In very low light, you can see. Right? There are some people with that. Okay. Animals also. Right? Some animals have very, very sensitive eyes at night. Also next, to see a discontinuous nature of the beam, right, you need to be able to see it very quickly. In the human eye, there's what we call the persistence of the image. Have you ever done the Facebook game thing or the online thing where you look at the image, you stare at it at one point, you don't move, and then you look at a white wall and you see the after image? Do you have that? Have you ever done that? Yes. That's because your eye, the image persists in your eyes, your cones and the retinas, right? It persists, right? In fact, your cone, there are 3 cones, there are red, green, blue cones, right? Anyway, the image persists, right? The things compensates, your eye compensates for the light that you see and then thus reduces that. But when you look away at the even color, then it comes out, right? So you can actually look at the inverse color of something and stare at it, and suddenly when you look away, you see the correct color of the picture. Right? That's because of your cones have compensated for it. So that's persistence of the nature of seeing, but it also stops you from seeing the discontinuous nature. Okay? Also, you'll be a terrible life, right? Because you cannot watch a movie properly. A movie screens at around 25 frames per second. If you can see that First, you're superhuman. I congratulate you, you are superhuman. But then I also very sad for you. Because when you're watching a movie, what is actually happening is you're seeing everything frame by frame. You'll be picture, darkness, picture, darkness, picture, darkness, picture, darkness, picture, darkness. Oh, horrible. But you'll probably be a very good sports person when racket sports. You can process the ping pong speed at 35 frames per second. You can, wow, your angle, you're not scared. How it spins, you can process that. Quite amazing. Okay. Next, what do you understand by the work function of a metal? Okay, this is just copy, right? Why are different metals work function different? That depends on the structure of the metal. Some metals, they hold on to their electrons more closely, right? Some metals, they hold on to the electrons more closely. That's why their work functions are higher. Right? So those metals are like copper, aluminium. Those, they don't like to hold on to the electrons. They are like cesium, sodium. Okay, they give out more readily. Okay? Right, that's it for question 1. Let's look at question 2. Okay. Question 2. In the photoelectric emission experiment, a metal surface evacuated tube was illuminated with monochromatic light. If it's repeated with light of the same wavelength but twice the intensity, oh, this is exactly what I've asked you just now. What will happen to the photon energy? What will happen to the Ke of the electrons, work function of metal, and photocurrent? Okay, I give you 2 minutes to try. Those of you who are done with question 2, you can go and do question 3 and then question 4. Okay? If you've done everything already, then you can do your own reading and wait until I go through, okay? Okay, right. So in the whole chapter, right, this one you must be able to answer because the whole idea of this photoelectric effect is to show the particle nature of light, which means that the energy of a photon is given by, as calculated by Planck, is E equals to hf. Right? So if you increase the intensity, do you change f? You don't. The frequency stays the same. It's the same frequency. So A, the photon energy, must stay the same. The work function of the metal depends on the metal. Changing the frequency changing the intensity does nothing. So A and C stays the same. So if your incoming energy, the photon, is the same, the amount of energy you put to the metal is the same, what can you say about the maximum speed of electrons? It will be the same. Einstein's photoelectric effect equation. So the only thing that changed will be part D. Okay, so let's look at the answer. So part 2 ABC, answer stays the same. Oh, it's really question 3. So ABC stays the same, unchanged, same, right? Not affected. Part D, it will actually increase. If you double the intensity, you keep the frequency the same, the energy stays the same. What you change is the rate of arrival of photons. If the rate of arrival of photons increase or doubles, the rate of emission of electrons doubles, your current will double. Okay, that is part D. This logical argument you must know. Okay, you must know. Right. Question number 3. Question number 3, which is the increasing order of magnitude. This one is very easy. Either you know or you don't know. Right? First, there are two things. One, you must know E equals to HF, which is this whole lecture. Second, you must recall into waves, right? How are these frequencies? So, the higher the frequency, the higher the energy. The higher the frequency, the lower the wavelength. So, if you want increasing frequency, you want decreasing wavelength. Okay? So here, this one is a mostly bookwork kind of thing. X-ray photon, the wavelength is about 10 to the power minus 10. It's very, very, very small. Sodium lamp, yellow light is about, I don't know, in the realm of 10 to the power minus 7. So you have 10 to the power minus 10, which is the shortest wavelength, highest energy. 10 to the power minus 7, the second shortest, second highest energy. Wavelength 3 meter, the longest wavelength, the lowest energy. So answer is 1, 3, 2. 1, 3, 2. Answer is B. Okay, answer is B. Number 4. Okay, you all want to see the answer? Number 3. You want to see or not? Okay, all like that. E equals HF only. Alright, so number 4. Can you try? Number 4, you must use Einstein's equation and try to solve this. Okay? 2 minutes, go. K times up. So they ask you maximum K depends on what? Wow, the equation is obvious, it jumps out. Once you write down the equation, the answer jumps out at you. Okay, so write down the equation. What do you get? Right, you write out the equation, you see this, and you see that none of it depends on intensity. Right, so answer is C. Depends only on frequency and work function. The lower the work function, the higher the K. The higher the frequency, the higher the K. Okay? Yep. I will not do number 5. I think time is about up. I don't think I have enough time to carry number 5 through. So go and do 5 onwards to the end. Let your teachers know where we stop. Okay, I also tell them, but you also let them know. That's all. Thank you very much. Bye-bye. If you have questions, please come down.